2009, I have started working in this field.
This meeting is being recorded.
Sorry for that. Yeah. So I took this research to operation to research approach, and there is a reason for that. Before that, I used to tell like all the Balaji told, like, yeah, I'm a kind of happy chance. I was like, in my master's, my specialization is actual statistics, which is the core of insurance. So I was doing very different work, and suddenly life changed. And then I started learning. I'm still learning the climate throughout like last 10 years, and now I call myself a climate statistician, which is again a very outliers term. Like in statistics there's biostatistician and others, but they don't know what is climate stats. Yeah. So as we are statistician, mathematician, we love to decompose our formula. So I started decomposing my title. So it's like a huge big title. So let's decompose it. Like, what does it mean by research to operation to research? So it, like Andrea is here, she's like expert on that, but I'm trying to explain the way I learn. It's like my experience. Like I work in four bubbles. The first one, I'm a core statistician, machine learning people working on climate model output statistics, probability, verification. That's my core. While I'm working on that, due to my experience, I also joined different institute where I work like operational forecaster, where I need to predict the things in a real time, which is putting your finger in a fire. Because if something happened after 2 days or 3 months, people come back and tell you, oh, your forecast is not working. So I was there. And then while I'm working there, I work with the stakeholders. When I say the stakeholder, that means I work with agromet, hydromet, climate and health, energy, those people. And that's a huge, I think, learning experience for me, because up to these two bubbles is all theoretical, and I do publish papers and all kind of verification we do in our research. But the real verification comes when I work with stakeholders, especially in agriculture and the health, energy, those area. While working on that, I also part of a different capacity building. Like as I was working in IRI, where my friend Nathan was also there. So we do a lot of capacity building in throughout the world, and that's also another huge learning experience, because when we start like teach something, we learn that how much less we know. So we keep on working on that. So that's something I want to mean by R2O2R. And as we all know, but just to, like for me at least, I was so confused before I start what is climate prediction and what is climate projection. So the way I understand, the projection means you're projecting something in future, in 100 years or 200 years, or the changes. You are not so detailed on each things. You are kind of thinking about how much the emission changes and what is the effect. That's called the climate projection. The climate prediction is different. When I say the climate prediction, it's kind of a seasonal or sub-seasonal prediction. So what will be like in like now is like September, right? So what will be next season? When I say the next season, it's like is the average of 3 months or 2 months or 6 months, depending on where you are in the world. Let's say winter focus, summer focus. So that's the kind of a basic difference. And as I'm belonging to NOAA, affiliated by NOAA, so NOAA has a climate forecast in their website. It's either sub-seasonal forecast or seasonal forecast. So that's kind of difference between prediction projection. Let's come back to my core, statistical learning. So the last one, to decompose it. The way I understand, like, since I was a student of statistics in 2003, and I don't even realize that statistics name has been changed over the years, and people talk about machine learning and data science. Well, like, I was like, what is that? Anyway, so that's what I don't use the AI or ML term. I use statistical learning term, SL. And I think Balaji also used the same term. So the way I understand is like, I'm not working in a machine learning core. Rather, I was working on some part of machine learning, which is based on statistics. And that's what I call statistical learning. It's kind of combination of statistics and core machine learning. Just want to explain my journey, because now the reason I put the slide, because I do have experience of teaching student, and now the first thing people come and say like, sir, I want to do something on machine learning. So like it was such a buzzword nowadays. So just to experience, like when I was like working on, let's say 2009, I was thinking about machine learning, and I was reading some of the papers, and I found like, oh, like, I don't even understand. It's like so sci-fi kind of term. It's like so, when I search machine learning in Google 2009, those things are coming actually. And then I start reading some papers, which is totally black box. I don't understand what is, convolutional neural network. That term I never read in my statistics class. So then I started working with different people like electrical engineers, civil engineers, and core machine learning people, and kind of asking the same question everyone. The answer I got, which is very related to this story. Like, there's a story like, for blind people, they're touching an elephant and everybody says their perspective. And I got the exactly same kind of experience when I talk with the people because they explain their experience. And then throughout the last 10 years, studying different papers, working on that, here is my realization. Like, as as per my understanding, like machine learning is actually a mask on statistics. So pardon me for any core machine learning group people. So anyway, so that's the point. Let's come back to today's discussion. First part, I will talk about the construction of probabilistic prediction in the sub-seasonal to seasonal scale. And I have a huge domain from the globe to part of the world like Africa and South Asia where I work actively. And the second part I will talk about very small domain, which is in New York City. And that's that my postdoc with Alan Fry, he mentioned, where we work for the climate change projection for New York City water supply. So the approach I took, this, no, the approach I took is this. So what I understand throughout the years, like the domain knowledge is so important because if you don't know what we're going to do, choosing a mathematical model or statistical model or machine learning model is very tough. So that's what I kind of spend a lot of time to understand, and I'm still learning this thing. So come back to the first part, the construction of probabilistic prediction in the sub-seasonal to seasonal scale. But before going to explain what route I took, I just want to explain like any kind of forecasting has two different things. One is the scale, and one is like what make them skillful or what is the predictability of that prediction, right? So the biggest predictability in the seasonal scale is ENSO. And again, I'm not the person to explain ENSO. Nathan is sitting here, his PhD on that. But yeah, so ENSO is like a phenomena on sea surface temperature, which impact a lot in different seasons throughout the world. It's not everywhere the same. And mostly I was talking rainfall. So this is like a teleconnection map, a subjective map. Whenever there is a temperature high in tropical Pacific, how it impacts. So that's kind of seasonal scale. There's also other. For the subseasonal scale, there's a wave called meridional oscillation, which also impact a lot. When I say the subseasonal, it is actually from week 2 to week 6. That's the or week 5 some point. So that's the time period. So, and also want to explain like what we expect. Like, okay, so that's the predictability. Now we do some prediction, but what is the skill of prediction? And as we all know about this cartoon, like after 3-4 days, any further forecast is kind of, that doesn't make any sense. And there is a reason for that because persistence doesn't work after 5 days. So there is again a hypothetical map. Like if you look at a map, it's not very quantified, but the x-axis is the time scale, the y-axis is like a forecast skill. So any weather forecast is very skillful in 1 to 2 days and then suddenly drop down because of a lot of persistence problem. And then there is some skill in seasonal scale because when you say the season, we take a bigger average of let's say 90 days or 120 days. So you're kind of smoothing this daily fluctuation. So obviously your prediction has some skill. But there's the biggest challenge in the between like days and the season, we call subseason. There's still a lot of things to do it. Come back to the what actually the literature talk about how we make the climate forecast. Obviously, there's a two different way to do it. One simple thing, you have a data, you just do a statistical modeling or time series analysis. Like you have a rainfall data from last 60 years, you just feed a autoregressive model. Or if you know what make rainfall happen, let's say ENSO or wind, you can make a correlation-based, regression-based model to make it. But none of this actually work because one, the autocorrelation of rainfall is very, very pure, most of the cases. And second, the relationship between the predictors and predictor are going to change because we talk about climate change, right? So the teleconnection between ENSO and rainfall in 1980s is not same as 2000s. So we can't use, those kind of things. And also there is a lack of physical process behind that. So that's what the people come with this general circulation model, which is basically you are actually solving this, different equations for conservation of momentum and others for each grid, and you're trying to mimic a whole atmosphere or climate with this, mathematical model. So that's what we kind of choose the other part, the dynamical model, because dynamical model has a lot of physical processes. But do we need only one climate model, or we need several climate models? So that was the question actually asked by my PhD supervisor back in 2009. And that's a very, I want to give a real-time example. So actually in May 2009, I joined in, I think in January. So he asked me, okay, so what is the forecast for upcoming monsoon? And I belong to India. So India, the monsoon is biggest thing. So we look different general circulation model that time. Like that's the forecast for June to September at May. And I got so confused to actually to believe like what should be in the future, because I don't even know. Every maps looks different. And then after the season, back I think in October or November, we got that rainfall actual value. And I plot it in an anomaly. That means like plus minus, like anything like anomaly means like plus minus to climatology, anything better than like anything in a blue, I think more than climatology and less than climatology. So that actually triggered me a kind of idea like instead of using a one GCM, we should use a lot like all the GCMs to make some kind of combination which is close to the reality. So that's called the multi-model ensemble in this field. Now, what are the common methods available? Yeah, there is mostly people talk about deterministic, not even probabilistic. Deterministic means like a one single value forecast, right? So there's a lot of research already done back in 2010. And what I found, mostly people use either average or do a regression. And there's a paper, is a very famous paper in 2000 by T.N. Krishnamurthy, Florida State University, about super ensemble. He called super ensemble, which is a kind of a linear regression based on singular value decomposition on the deterministic. But I was still looking for my answer because I think the seasonal or subseasonal focus should be probabilistic. So there is no literature available that time. So working on that, I was like, started step by step. So thinking about how we make a probability for a single GCM, because the GCM give you a forecast, which is deterministic. So first we have to find the probability from each GCM, then we go for the multi-model. So the non-parametric way, okay. So when I call climate models, the way climate model run, it run with several initial condition and boundary condition. That means like it's basically try to solve the differential equation within the climate model by different iteration. And it started with different initial conditions. So they ended up with like so many different forecasts within a climate model that calls ensemble members. So now, for example, if we know that there's a 3 category or 5 category of forecast we're looking for, we can simply count how many members fall each category and just take the like just divide by the total number of probability. So that's called kind of non-parametric simple way. Second way, people use some kind of a parametric like modeling. For example, you take the deterministic forecast for climate model and you kind of convert it in a probability distribution, mostly normal distribution, and then you get some kind of probability. So that's kind of two generally methods available in the literature. And once you get the probability from each GCM, let's say this is the P of probability of each GCM, then we need to find some kind of weights to give the weighting. And again, the weight can be done, this whole probability method, multi-model method can be done both way, deterministic non-parametric and parametric. So I have tried different approach to find these weights, a lot of different approach. And I'll come back like what the limitation of that approach. Again, different way to calculate the distribution, how you make this option to make the spread of the distribution, a lot of mathematical work behind that. But what I found, mostly the reason I was thinking about moving towards machine learning, like what is the limitation of this tool? First limitation is if we have less number of ensembles, we always kind of overestimate our probability. Second, in parametric, like in real world, like all the we statisticians love to assume normal distribution everywhere, thinking about central limit theorem, but actually it's not. In real life, nothing is normal, at least for the rainfall. So it doesn't work. So what should work? So we're thinking again, like step by step, like before move to the machine learning, like just think about quantile regression approach. Although like people talk that logistic regression or quantile regression is also a kind of machine learning, but I'm not going to that discussion, but I start taking quantile regression and then, kind of advance. So as we all know about this equation, maybe like logistic regression, like here, the important thing is like you don't have to convert a deterministic forecast to probability. Logistic regression, it's a regression between a continuous data and a dichotomous data. That means you can think about a classification problem. If it is rainfall, whether it's you give the input of the real value of rainfall and you make a categories and you can find the probability for each category. So thinking about this simple logistic regression, and I started working on that, but then I kind of found on paper and also I experienced this thing by my own research, like logistic regression for each threshold or each category can be fit independently. So that means suppose you want to predict for 5 category forecasts like low, medium, high, heavy, those kind of category or more. But logistic regression fit in different category independently. When you plot the quantiles or those categories, always there is a chance that the probability from the lower quantile is higher than the higher quantile because it's all kind of, because there's no information. In simple way, logistic regression doesn't give a full probability distribution. That's what we are thinking about this idea. Again, it's Wilk's paper. He called extended logistic regression, but as a student of statistics, I called it multinomial logistic regression. So you're actually adding more predictors in the equation and adding a quantiles as a function of logistic regression. Instead of predicting for each threshold category, you can actually predict for multiple category in the same thing. So that's called ELR methods. So, and when you plot this like probability, you can find these parallel lines. So I took this approach back in 2000, most probably 17, and implemented at IRI where I used to postdoc at that time. And we changed this whole method, and still IRI using same idea, and we kind of move their old method to new method, and this is like real time. What the skill, like there's a different way to show the skill, and each and every naming of the skill matrix need maybe uh, 30 minutes to explain. But just to explain here what we plot RPSS, which is called rank probability skill score, which is simple way if you think a quadratic difference between probability issued and whether it's happened or not. Let's say you give a probability of something zero point 0.7, and if it happened, it's 1, if not happened, it's 0. So you can calculate those differences, and in somehow we can combine all the category together and make some kind of RPSS. And we always like, probability skill score, you always compare with some kind of reference forecast. And in seasonal scale, we use the climatological odds. That means you have a climatological data, you can calculate the frequency and calculate the probability of each category. So that's the RPSS, kind of same kind of skill score, but on the logarithm scale. And then reliability, rock is very common in machine learning, where we kind of find like hit versus miss. So we do a lot of different kind of skill score and find this ELR kind of method is actually working. But the point here again, what I found, I kind of fitting this ELR for each grade independently. When I say the grade, that special grade. So there is no information between two different grades. So if biggest event happen, it should not happen only one grade. It should happen surrounding grade. So we need a lot of post processing after that, and that's what I choose, like kind of a spatial smoothing, and I use a kernel smoothing on that. Like think about before smoothing and after smoothing, you can see the difference. So there is no kind of funny probability like one grid have below or one grid is above after you smooth the probability on that. Does it does it affect the skill? We also find like, okay, what's the difference if we put the smoothing and without smoothing? We don't find biggest difference. So that means it's okay that smoothing doesn't spoil our things. So that's the way we took it in back in 2017. But again, come back to the research to operation, this approach. When you present this forecast to the stakeholders, agriculture, hydrologists, renewable energies, they see like they don't find too much information. The reason behind that, if you look this plot over Africa, it gives you a overall idea about 3 category probability. Now, suppose you are working in a disaster management and you want to see what is the chances of heavy rainfall in season or drought in season so that you can make your contingency plan, you can't use this kind of focus. That's what we choose, a flexible format, or in any like one sense, if you just click any grade, you can get whole the full PDF. And that's the whole point I started ELR. And here, the black and the blue, the green, the black line is like the climatological probability. Like for suppose you don't have forecast and you have a data, you make the probability from the data and how differ the forecast, which is green. And from this point, you can get the probability of each and every threshold you're looking for, and also compare how much the probability from the GCM actually telling you compared to the climatology. And there's a huge application of that. I just want to show one of the application by forecast-based financing team at IRI back in 2020, I think. So they use this thing over Malawi, and they actually make different triggering for different probability so that they make the insurance based on the forecast. So that's one of the example, and that's what I really acknowledge our application team who actually helped me to understand what should be the product I should generate it. Now coming to the substantial scale, same method which we use for sub-X model, and that is something going on right now at NOAA CPC. They use it, but what we found in a simple way that after 3 weeks, the scale is not that. And that is not the problem with the post-processing. It's general. As we have already shown the map, like in that scale, the getting the prediction signal is very high, like very tough actually. So that's kind of our journey with the logistic regression. Then I thought, okay, so let's do a little bit of complex on that. And I was thinking about what should we do. The biggest constraint actually in climate forecast is we don't have a huge data set to run a deep learning. And you can run anything, but it's all about overestimation or overfitting. So we have to choose a method such a way that it's not overfitting. That's what I start with, very simple thing. As you all know, like single feed forward neural network. I'll come on that, but before that, the whole point, what I envision, that suppose you have a lot of GCMs, you do some kind of statistical learning, your target should be having a probability distribution. So that way you started, working on that. But before that, like I think we started this probability machine learning 2 years back, but back in 2014, I was thinking the same problem, but in a deterministic perspective. Suppose you have different climate model, instead of doing simple linear regression, can you do some kind of machine learning which actually like outperform the regression? And this is the paper we published 2014. It's a shameless promotion, but I want to put it here because back in 2014, it was so tough to publish a paper using machine learning because there's no reviewer. So I remember this paper communicated at 2012 end, but it took forever to publish it because the people don't find the reviewer anyway. So that's the kind of skill we got. Like if you think about the box plot, which is a different way to show your forecast, and this is the observation. This is a simple average when you just average the climate model, and this is linear regression based on singular value decomposition, and that's kind of a method we took, which is a generalized format of single fit forward method called extreme learning machine. And the biggest thing I really like, I'm not interested too much like the correlation and this thing, I really like the spread, and we need that spread for the probability. So I kind of go back to my earlier paper, I was thinking, yes, we can actually use this method. But before I go like how I explain, but just a little bit of thing, like again, the biggest the good thing in the ELM is it doesn't take too much time to fit because it's not actually fully connected network. It's actually start with some random bias and random weights in the first layer, and then it's all about a kind of a generalized linear model. If you look about this part, so it start with the random weights, random bias, and it's all like, and then you put some activation function, and it's look like a very generalized linear model. Although it's not linear regression because it's not, if you solve linear regression on this equation, you cannot solve it because there's a lot of problem of singularity. So we use G inverse on that. So in short way to tell, like because it's not backpropagate and update the weights, it's actually much lesser time took, and we need a lesser time uh, constraint neural network kind of things because we are working on real time. We can't wait forever to get the forecast. So that's what I took this ELM. Now the question is, can this simple ELM make the probability? That's kind of theoretical question, and we don't find it because the limitation is like the traditional ELM only produce deterministic forecast. There's a paper recently, they make some kind of probabilistic output. So what they do, they actually change the the output layer's equation to a sigmoid function. And we thought maybe it actually solve our problem, but it's actually not. Because what happened, because if you look this function, it's exponential. So you need some kind of log to solve this problem. And in real time, we use y as like all the observation either happen or not. So it's either 0 and not 1. So if you take log of 0, that will be biggest problem. So, and also there's other problems. We kind of modify the whole method and change it. So, and also there's a biggest problem, like it's giving you 3 category forecast, but the summation doesn't show 1. So we need some kind of regularization on that. So kind of changing the method, we kind of testing it in different scale. So this is a kind of a method we choose for seasonal scale. We use kind of, North American multimodal or others, and to show the scale over Indian monsoon, because Indian monsoon is very, very hard to predict. So just to make sure that our forecast is kind of, some kind of scale you just apply there. We also take sub-seasonal scale recently, and we're kind of looking at different part of US whether it has any scale. And the model I choose here is ECMWF as input. And also while working on that, suddenly like 1 year back, there's a competition at ECMWF. They're looking for this kind of AI-based challenges on the post-processing. So we participate there and we kind of, show our methods. So that's kind of, whole talk on the global scale. I also want to explain a little bit of my work in different part of the global, where I work with National Meteorological and Hydrological Services to improve their forecast. Based on WMO's new norm, they call next generation forecast, which is based on objective function. So anyway, like it also depends my capacity building training, this and that. But one, like I work so many countries, but one country I want to show, which is in Bangladesh. Earlier they have a forecast like this, as text, and the stakeholders only have those text. It doesn't know what does it mean. To change their mindset and apply this kind of statistical machine learning method to there is a lot of management like management work. So I'm so happy they also started this real-time forecast, I think since 2019. And also I have like a lot of different country. I just want to mention these 3 different paper. One paper is something in Ethiopia. They also do the same kind of things, and they tested in different things and they published. And also, again, go back to my connection with the stakeholders, especially CEAT, CIMIT. Those are the institute who are working on either maize or rice or different crops, and or aquaculture. We're kind of making this kind of early warning system, or based on this forecast for aquaculture, or how to define the onset of a rainfall season, because the onset has a different kind of definition. It have a dynamical definition. It also have a tailoring definition based on different crops. So we did a lot of work on that. So quickly, I don't have much time, but the another thing as a academician, we found like, okay, I do a lot of paper, I do a lot of published paper, like things, but it cannot be translated proper way if I don't have any tool to actually prepare, so that people who don't have much programming background, machine learning background, still understand the method and run it. So we work on that with my colleague Kyle. We make a package called XCast. The name is very interesting. The cast come from forecast or hindcast. X come from the X array of the Python. So this is something like website we kind of make, and we kind of support thoroughly. We have a lot of different options there, simple statistics to advanced machine learning, then verification, this and that. So the way it works, it could do pre-processing, post-processing, but just the point I want to highlight this part, the chunk-wise parallelism, because what happened when you run up machine learning, it took a lot of computational power. And I was thinking, because I was in Penn State and kind of an assistant professor, I was working with the student, and student have laptop. They don't have kind of cluster or HPC. So thinking about how to make this tool which can work for laptop to the cluster. So we took a Dusk like parallel process, if you know that is from the Python, so that each grid goes in different node and calculate at the same time. So we spend a lot of time to make this tool, so that, and also like we use this tool to make a real-time forecast on the forum by WMO called South Asian Climate Outlook Forum. So we make this thing, and in fact today morning I have a presentation at WMO Lisbon on this. They have a program going on called Operational Climate Prediction. So slowly, like this tool may be used by the different country on that. Okay, so conclude this part. So non-parametric, parametric, different approach for the probabilistic multimodal, but we choose machine learning, which is kind of used as a white box. We know what we're doing inside and actually implement such a way there is no assumption on both the method, parametric, non-parametric. So that's the first part. The second part is like climate projection part. What I have done for making this, again, statistical learning based climate projection, and here maybe interesting. So after my PhD, I was looking for postdoc and I was looking for this climate forecast and nobody gave me any job. But suddenly I got a job from New York City and where they want to know what is the impact of climate change of their water supply. Interestingly, like, I don't know how many of you from the New York City, the whole drinking water of New York City comes from the upstate reservoirs. And it's a very, you know, there's no huge money involved to the filtration of the water. It's like very normal process. So and the source of this water actually snow melt and the rainfall. So they want to see what is the impact of climate change on the quality and the quantity of this water. And there's a lot of study already published on northeastern part of US going to be more heavy rain and those kind of things. So like generally say, oh, there's a lot of rain, so there's no problem because you can get a lot of water. But there's a problem on the heavy storm. Like if there's a lot of storm, then this whole reservoir surrounded by these woods, and there's a lot of problem on increase the nutrition loads and annual cycle. So heavy rainfall is also very dangerous from the water supply system. So most of the people took the approach, as you maybe know about climate downscaling approach, take one climate model, downscale it, and make something. But the biggest problem, this particular region is so small. If you look the grid size of climate model, it doesn't fit. So that's traditional top-down approach doesn't work. So that's what we choose kind of a bottom-up approach, which is instead of looking from the top, you actually thinking about the system vulnerability from the domain, and then you upscale it. And on that, the biggest tool on this bottom-up approach is stochastic weather generator, which is, I feel very shy to explain this stochastic weather generator in front of Balaji because he's like guru on that. So Balaji, please, you may say so a lot of thing, so you may tell me if I'm wrong any point. So the way I understand stochastic weather generator is kind of a statistical model which is based on a data. Suppose you have a data from some area from last 100 years. So the easy thing you can do, you can find the probability distribution function of this data, and then you just generate the data from that probability distribution. And those data may be random noise, but their statistics is same as the data you give to make this PDF. So that's what they call weather generators, which is not weather forecast. Weather forecast, each and every simulation of weather forecast is actually based on the physical process. But here, it's actually random noise. But if you look in the bigger picture, the statistics of that random noise is same as the statistics of the rainfall repeated. So there's a lot of application and a lot of study already happened. And I was like looking the literature and I found the first paper published in 18th centuries. But most of the people choose this Richardsonian method, which is published in 1980. So the way it works, suppose you are thinking about rainfall. So when you're thinking of rainfall, it's such a random variable. It has discrete and the continuous characteristic. Discrete means whether it's rain or not, right? So you have to first make that model whether it's rainy or no rainy days. And once it's rainy days, then you make some kind of distributional approach to make this rainfall. So that's kind of classical approach, but there's another approach like Balaji and Manu, they are taking this KNN resampling method, which is instead of going this parametric method, you can do this resample. So the goal we took there, first of all, this weather generator should be very localized because the data is different for different part of the world. So as we're dealing with the New York City water, we're thinking about what is the best weather generator. So first job, find the best one. Then we run the watershed model, and then we do the future projection. So that's like a 3 different approach. So the first approach where I involved a lot to find a kind of a best combination of weather generator based on occurrence process and amount process. So occurrence, we mostly take the Markov model, which is probability of if you think about Markov model, like what is the probability of a time series, like suppose you have a sequence of random variable, you want to probability, like what is the probability the next random variable based on the whole data is same as the immediate data. So we kind of use different order. So when you put different order, that means you want to use different memory of the rainfall data. And then we choose different distributional approach, is parametric. We also choose Balaji's KNN method, resampling, and also we try to do some kind of like curve fitting method. So while doing this thing, we have a lot of results. Like the result we found is like all the orders in Markov chain look same. That means there is no particular season for rainfall in New York City. Like for example, it is in Indian monsoon. We can see like maybe there's a long dry spell, so maybe order of 3 is good than the order of 1. But New York City is like almost every day we get some kind of rain or the snow. So we don't find any difference between the order. Also for the and this, for different watershed, you also find that the descriptive statistics of the rainfall doesn't impact a lot, whatever the weather generator you choose. Then we started looking at the extremes, like, that WMO has some kind of definition of extreme indexes. We just plotting and found, there we found the difference of using different kind of weather generator. Looking a little bit of, the simple way to find it out, like I just plot the empirical distribution of the observation, which is black here, and two weather generator, which is based on gamma distribution and beta distribution. You can see the difference in the extremes. So maybe they are good in the central tendency part, but tail of the distribution, nothing works. That's what the reason we put different way, and we found some of like complicated weather generator really work. We also tried, because we are talking about watershed people, they are interested on this flood return period. So we kind of put this generalized extreme value distribution of each uh, output of weather generator as well as the observation to find which one is actually close to the observation. So we do a lot of kind of statistical post processing to find which one is good. After that, we found maybe Markov chain 1 and skewed normal distribution. This combination is good, and based on that weather generator, we run the watershed model. But before making that projection, the first thing we try to verify the second stage. The first stage is verify just weather generator. Second stage is verify, okay, there is a hydrology model. You can run the hydrology model with the observed climatology, or you can run with the weather generator data. And is there any difference? So we run the GWLF watershed model based on this of last 60 years of data, and also the data generated by the weather generator, and for each and every watershed. And we found this weather generator based uh, output from the watershed model is as same as the climatology. So we kind of confident that yes, so the response variable, which is stream flow, is also simulated quite good. So based on that, we kind of use, like, this is our baseline. That means use last climate and make something. Now we do a lot of different approach. For example, what will be the rainfall is, more than 115% or less than 15%, which is 85%, or what will be the temperature changes from -1 to 6 degrees Celsius. With that different approach, we run our weather generator. We also plot climate model output and all the other flood and drought happen, and try to understand this three-dimensional plot, like how we can actually produce more climate change projection, which is not only constant on the climate model. But while working on that, one thing as biggest problem we found, which is that the single site versus multi-site. So what the way we run here, like if you look this 6 different watershed, we feed different weather generator for independently. So there's no information between the sites. So if there is a storm happen, it's not only one site, it's also impact other site. So we are thinking about having a multi-site weather generators. And although like there's very few paper published on that, but I was a little confused about, because people again do a lot of assumptions. So I was thinking, okay, let's do something on machine learning. And because we know that there is a machine learning community where like you can use the generative model. So that's what I was thinking, to use this model, which we call GAN, which is Generative Adversarial Network. It's a very interesting model, and I can explain with this cartoon. Like the one part of this network generate a data from the random noise. The other part, which is we call police or discriminator, is actually trained by the observation. So he understands what is real, which is fake. So think about this is a Mona Lisa picture, which is he know how it looks, and somebody want to make it, and he's not satisfied up to he make this thing look like this. So this whole network has a two part of neural network. That's what we call semi-supervised. One generate the data from random noise. One's already trained with the climate data, so he know what is fake, what is real, and it's kind of adversarial game going on. And just looking at the equation, the first part where the discriminator prediction is actually you are actually trained a neural network based on the observation. The second part, actually the generator who try to fool this discriminator, but the discriminator is kind of a police you don't want to fool. So basically it's kind of a min-max problem within this network, and it's going on and doesn't need any parametric. So basically what we do, we start from there and we end here. So we start from the random noise, we end with a weather generator. So that's something we are very interested to do, because there is no parametric assumption, there is no resampling thing to happen. So, and also we can run this whole weather generator based on all the data from different watersheds, so that they keep this spatial correlation together. A little bit of the way we make this thing. I don't want to explain this thing, a lot of technical issue, but come back to the result side. So this is the box plot from the actual data. Suppose you have a 60 years of data, you can calculate the box plot from each watershed model. You can also use the synthetic data, which is come from this GAN based weather generator. It look very simple, although we're interested on the extremes. The extremes also look very close, but what you're really interested is this plot. If you calculate this cross correlation between the watershed, you can end up with this kind of heat map. And what we really want this. So this is a synthetic data, which is based on this multi-site GAN, which is looks similar. Again, I'm not playing too much on hyperparameter tuning here. I just start to understand whether it works or not. So the simple hyperparameter tuning shows kind of promising results. So in future, this result can be much better if you do kind of a objective way to hyperparameter. So the remarks, we use bottom-up approach, but we found that we need a multi-sites. That's what we moved to the advanced machine learning. So that's kind of things. And a little bit, I want to explain what I'm doing right now at Series PSL. I was working on different scale, basically all three different scale. One, weather forecast, which is we're working on wind and solar renewable energy using Dept version 12, using machine learning based post-processing from 6 hourly to 10 days. Second, I was developing a kind of a machine learning based seasonal forecast for our partner at FuseNet, which is focusing on Africa and Central Asia. And the other part I was working on with the California water supply, DWR, I forgot the full name, like how to construct a subseasonal focus. So basically weather, subseason, and season, not much on the climate change. So I think that's the end of the talk. And just to know a little bit of take-home message, I have two take-home message here. One, this thing, like I don't like when I start, people thought like either I'm a magician or I don't know anything, because I'm come from statistics. So statistics can do anything, or or you don't know anything because you are not studying the climate physics. So kind of the way I thought myself to be a climatologist, like this cartoon, like you have to understand the domain knowledge, but there's no need like one person should know everything. So there is a collaborations, right? And there's an excellent US talk on that, how a data scientist and a climate scientist collaborate together to make a team. And that's what I mostly like, thanks all my collaborators, whatever I learned because of them, in fact, from the students. And the second, which is really, really important, using machine learning, because we need to use machine learning without any understanding. I'm really interested to use this black box as a glass box or white box. You have to understand the maths, because the reason people thought this black box, because they don't understand the amount of linear algebra and amount of statistics behind the machine learning. And I think we need to know, otherwise it's all like, just switching here and there, playing a video game, different level. On that, thank you very much. And this is not something I make, it's from the random forest. So machine learning looks very nice if you look in a different way. So this is a decision tree based on random forest, and it looks so nice. And so I thought, oh, let's, instead of putting a flower, let me put something on from the machine learning. Thank you very much.
Okay, we have time for questions. And people in the Zoom world can unmute and ask away.
Good question.
Go ahead.
Thanks for your presentation. I was interested in
Microphone.
Yeah, so that middle section when you were talking about the weather generators and how your domain that you were looking at was too small to use GCMs. And so I'm wondering about how you're comparing the weather generator rainfall to the actual rainfall, but then I think what you're trying to get at is a future climate rainfall and how to, you have the GCM output, which is at a different scale. So how you compare it with the
Yeah, no,
future
that's really
climate.
very good question. I should go back to this plot, which help us explain. So if you think about just using weather generator, using past data, we are not changing anything for the future. That's what we call baseline, like 100% rain or 0% change in temperature. But you can actually run the weather generator in different scenario, like 110% rainfall or 2 degrees Celsius. But that generation should not come randomly. Because I'm working with those people, those hydrologists who was working like 30 years on this part, they have a lot of knowledge, like what they're expecting. For example, 1960, there is a big drought in New York City. So they're thinking about those kind of, because none of the climate model give that kind of explanation like this 1916 drought. And then coming back here, like once we generate the future generation with all those different things, we also downscale the climate model, which is the red here. And the downscaling part is we actually borrow from the NASA Nexus or something where they use kind of analogous. So if you think about the climate model only give you, like if we don't run the weather generator, climate model only give you this kind of generation, which is more rainfall and more temperature. But then you miss those 1960s drought or 1980s rainfall. So that's the reason, like we make the model, we run future generation with different combination. We also see what is the climate model and what is the past history. And then they took the decision. It's kind of, that's why it's called like, system vulnerability. You look all the different perspective rather just climate model, which is based on this emission scenario. I hope this is the answer. I don't know. Yeah. Okay.
Hi, Nachiketa.
Hi.
Presentation, sorry, I got here a little late. So I have like 3 comments. So what you show here is exactly something. So I'm at the Bureau of Reclamation. So we're kind of doing something very similar.
Okay.
So the weather generation being guided by a downscale climate projection information. And the weather generator we have basically has essentially 3 controls on changes in precipitation amount, and of course, changes in temperature, and also shifts in seasonality.
Yes.
Precipitation, mostly working in the US Southwest. So that's I just wanted to say that we are trying to do something very similar. The second comment for me is, so when you were talking about the multi-site weather generator versus single site, so this is way back 2004, and Professor Balaji, we were together working on this. So possibly you may have even seen that paper called Shaki Shuffle. And
Yes.
So that was the whole idea on how, because we were doing downscaling using multiple linear regression at that time.
Yes.
To various hydrologic units, right? So how do we then take and preserve the spatial covariability? That might be something you want to look into, because it's very straightforward, because it essentially is preserving the Spearman rank correlation. So that's what it is. And my third comment is, you talked about GV, and I see that GV being used extensively for precipitation frequency type analysis. But when you're coming to the hydrology side, and especially extreme value analysis, the GV is not a realistic model for a physical hydrologic setting. There is a reason why here we use the log Pearson type 3. Yeah, people can be critical about it, but it's a model that works pretty well for our dam safety type analysis.
But Totally agree with all the points. Just a few comments. Yeah, so I know that paper actually. Uh, in fact, people after that, they published a paper on Bayesian network, copula, different kind of multi-site. And I was like, the more interest I have, like instead of like, if we just train this whole machine learning from random data to something, and it's actually very quick to predict, like training part is always taking time. So I compare with that things, again, the skill in terms of spatial covariability as same. So that one thing. And the last point, I forgot what you said. Yeah, I'm totally agree with that because what we found, GV based on the block maxima, right? And we mostly take that one singular maxima in a year, but there's so many different maxima. We also play with GPD. We also play with the other one, partial process. But here I just show the GV. Yeah, I totally agree what you said. Yeah.
Hi, thanks for the presentation. Really enjoyed it. I'm Nathan. I'm like a fourth year PhD student. I've worked with Balaji and Subrendu with TSC, so I don't do climatology type stuff, but I mostly work in water resources models. So I'm kind of like down at the very bottom of this uncertainty chain that you're talking about. And we also think about vulnerability assessments and the idea of like communicating in terms of probabilities to stakeholders. And in your experience, what are people's appetites for that? And I'm not talking about academics. I'm not talking about even, your average decision maker, just kind of people in the field and your experience working in these different contexts. What are kind of the stumbling blocks, the hurdles, and then their general appetite for thinking about their decisions in terms of probabilities?
That's great. Actually, like that, one of the thing I also struggle a lot during my PhD up to now to communicate forecast in a probability. Like most of the people, they understand like the deterministic aspect, but I'm fortunate to work with actually the farmers when I was at IRI. Nathan know that, and what I found, farmers, if I think about farmer as a stakeholder, they understand probability much better way than the middleman, which is the policymakers. I give you one example. Like I was visiting two different zone. One is drought zone, one is flooded zone in India. And I talked with a farmer lady, and she was talking about like climate change and the probability. How they like, she said, "Oh, there's a lot of climate change happen." And I thought like, "How you understand climate change?" She said like, 10 years back, the amount of money I put to get the water from the ground is less than 10 times now I give. That means it's actually the water storage. So they understand the climate change in terms of money. And she's asking me, like, we always make, they don't go for the one crop, they go the multi-crop. So kind of risk management in probability way, like we communicate like 45% above normal, but still there is, 35% of other part. So they do that way. But I feel extremely hard to communicate with Department of Agriculture Extension people to like communicate the probability. They don't understand actually. So I do I really interesting like this communication part. And also another thing I want to say, like I do a lot of communication on the media side, and that is also different thing. Like totally altogether. Media always want like kind of strong probability. In seasonal concept, we can't give a strong probability because of this mathematics behind. So it's always tough to explain somebody what is climatological odd. That means what is the 33 percentile for each category, and what is the probability. So it's, I think you are doing a really good part of the research, that how to communicate this uncertainty in the forecast. Great.
It is also interesting that the uncertainty part, individually, we all deal with it every day, right? And yet, when we want weather forecast or climate forecast, we want certainty. Right? So, but we are quite comfortable. I mean, simple example I use is even when you cross a street, you are looking at the traffic, oncoming traffic, and you make a judgment, and you make a decision whether to cross or not. If there isn't a traffic light, and those are all dealing with uncertainties, and you do that routinely all the time. But yet somehow when it comes to climate and weather, I remember in 2000 talking to reclamation folks. They, of course, this was back when all the reservoirs were full, and I told them, we can give you probabilistic. There's like, no, don't even come to us if you can't give exactly how much flow comes in. And it took a drought. 2 years later, they
Really close.
2 years later, they came to Connie Woodhouse. She was here at the time with bags of money. Can you like go code some trees and tell us how bad it can get? These were the same reclamation engineers who were like, don't even talk to me. So it's interesting how, and that is, I would say, is the most challenging part. It is more challenging on the climate side because with weather, you can play the game every day, right? So it's like, playing the slot machine over and over again. But whereas with climate, you don't get it this time, then you got to wait till next year. And so you're playing fewer games. So which means the uncertainty is even more important than weather concept, weather situation.
Balaji, I remember one thing, like one time somebody told, like, if you think about soccer game, like the whole game is like seasonal focused, and during the game, like the ball position is kind of weather kind of things. If you think that way, like, yeah.
Predicting that is,
Yeah,
and then there's uncertainty on the entire game. Yeah.
exactly.
Any other questions? I'm seeing if there's any on the chat,
No.
Zoom.
Yeah, I just want to say, so I'm a master's student in applied math. My undergrad was in environmental engineering, so this talk was definitely extremely inspiring. What do you find is the biggest hurdle in interdisciplinary research, and how did you overcome it?
Excellent question. That's my life. I should write a book on that. Because I can tell you the hurdle right now. I have people from the meteorology background, they don't take me seriously because I don't have meteorology. People from the statistics, they don't take me either because they tell, oh, you're doing the data analysis. It's not statistics. What is the new distribution you discover? I'm really telling you that's the thing happen right now. They don't understand the power of interdiscipline. And here, the power I found, I can talk with any of the community. I can talk with Andrea, I can talk with Balaji, I can talk with the statistician because I know the lingos and the way I kind of like that's what I call I'm the example of unsupervised learning because I don't have teacher. So the way I learn, seminar, conference, I'm so grateful the different authors in the paper. Whenever I read paper, I write the authors to understand the problem. And 90% of cases, they reply me, including this gentleman, Balaji here, in back 2010. I was reading his paper on Bayesian approach on climate model. I don't even understand anything. So I think like that's kind of a, obviously struggle, but also a sweetness that you understand the lingos and different things. You feel like, yeah, I understand what the climate people are talking. I understand what's theoretical statistician talking. I understand what climate machine learning people are talking. So it's kind of it's slow process, but at the end you will be win.
Yes, so keep doing what you're doing. And actually, this is a problem that's been there for more than 100 years. You probably know this. Walker, the famous Walker circulation,
Gilbert Walker
was a statistician. In fact, he was the first to come up with how to estimate parameters for autoregressive models. So we use, those of you might remember Walker equations, is that Walker. And he, of course, he also did a lot of work with with weather data and climate data. And he was the first director of the Indian Meteorological Service. So in 1920s, after the Bengal famine, he was asked by Her Majesty to go and find out what's going on. So he comes to India, and he was the first to employ correlation in meteorology. So all he did was looked at pressure maps from Australia and India when British colonies at the time, and he found something. Hey, whenever pressure goes up and down over Australia, the rainfall over India goes up and down. So he wrote a paper, 1925, Royal Meteorological Society. Yes,
yeah,
which is
exactly
still quoted to this day. And of course, throughout his life, obviously, both sides didn't like him. And long after he was gone, suddenly everybody's like, wow, now we know that was Southern Oscillation. Now we know that's what Walker found in those correlations. And so there is quite a bit of resurgence There's a centenary lecture. Katz, who's a statistician at NCAR, retired, gave a lecture there in that ceremony. So it's interesting that how everybody likes interdisciplinary, but when it actually comes to it, people are so parochial. Oh, you're not meteorologist or you're not statistician. But I will tell you, to echo and we'll end at, there is all the fun problems are at the intersection.
Yep.
So if you can take the time to learn 2 or 3 different fields, it's so much enriching and fun than being siloed in one. So.
But Balaji, I want to add on that worker things. Like you are from ISI, Indian Statistical Institute, right?
Yeah.
And you know who is founder.
Yeah,
Yeah.
he also did a lot of applied work.
He did in same time. He has a paper on 1930s on rainfall. Like he make this report for the British government for this drought. Like that paper published and it's actually in the library.
Yeah.
And when I was invited to ISI last year and they kind of try to understand what I'm doing, I show that paper. Like, look, like we're talking about monolithic distance, but nobody talk about monolithic people and rainfall. Yeah.
His first thing was Indian government wanted the census.
Yes.
So he figured out the sampling on
how to sample.
A newly formed nation.
Yeah.
With,
Interdisciplinary work is good.
Always helpful.
You ask the question, keep doing what you're doing. So on that note, thank you very much. Yeah.
Thanks. Do I need to leave? Yeah.